Can we increase the forced convective heat transfer capabilities of an extruded type heat sink with a simple and manufacturing-friendly turbulence promoter? In order to be manufacturing-friendly, the turbulence promoter must be incorporated into the extrusion process or be added afterwards extremely inexpensively. The extrusion process can make a single location feature, therefore it must be added afterwards. The solution under test is that of small bloop of metal at the channel entrance to act as a turbulence promoter. As seen in the animation, when the air enters the channel, it speeds up due to the decreased cross-sectional flow area, which increases the convective heat transfer coefficient. The turbulence promoters were theorized to increase the turbulence of the flow without slowing it enough such that the net effect on the convective heat transfer coefficient was positive. Because the entire crux of the simulation revolves around the added heat transferability of a turbulent flow, it was imperative that this be captured in the model. Therefore, the realizable K-epsilon model with enhanced wall treatment was used in Fluent. It models the effect of turbulent fluid structures using transport equations to capture the macro scale effects. The heat sink was placed inside of an enclosure with an incoming air velocity of only 0.5 meters per second at 20 degrees Celsius to stimulate simple electronics with only a small fan to provide airflow to the entire case. It is not intended to model an electronic component with a dedicated cooling fan. The major simplification was to the geometry of the model. The fins and turbulence promoting posts were entirely rectangular geometry in order to obtain a mesh capable of accuracy that remains within the element counts limit of the ANSYS educational license. In order to get a measure of the effective heat transfer, the heat sink was set to a temperature of 40 degrees Celsius, which is a warm running chip but below the typical maximum operating temperature of electronic components around 85 degrees Celsius. The temperature of the air at the outflow boundary was used to see if there was a significant difference between the two heat sink geometries. The enclosure boundary conditions were a no-slip condition and a no-heat flux boundary condition. The velocity vector graphs for the two geometries appear as expected. There is some decrease in the flow velocity due to the turbulence promoters. They do appear to cause a turbulent flow to develop within the heat sink channels. The temperature distribution of the air as it leaves the two heat sinks is similar, but the distribution coming off the heat sink with the turbulence promoters has a marginally more diffuse temperature distribution. The temperature of the fluid as it exited the chamber was then measured to determine which heat sink impaired the most thermal energy to the flow. The original heat sink configuration outperformed the configuration with the turbulence promoters by almost 6 degrees Kelvin with measured temperatures of 283.8 and 278 Kelvin respectively. The conclusion of the experiment is that the addition of the easy-to-manufacture turbulence promoters severely hampered the ability of the heat sink. This is most likely due to the decreasing velocity of the flow over the surface. If future experimentation is to be done, the recommendation is to apply this idea to a larger heat sink, such as those attached to a cooling fan for a single electronic component, such as a GPU.